To start off our unit on exponential and logarithmic functions, we are going to use this video to talk about exponential graphs. To really understand what a function is like, I think looking at a picture of its graph can help you do that. Exponential functions are different than the functions we've done so far. We've done quadratics and some higher degree and some irrational or square root type functions. Exponentials act in a different way. Exponentials are characterized by slow growth at the beginning and then kind of a tipping point after which the growth gets really, really steep. So when they say something's growing exponentially, you know that it's growing quickly. In general, let's call this general form or standard form. The equation has two parts other than the y and the x, the two variables. The a and the b, these parameters are going to determine some things about our graph. A is the y-intercept. It's like the starting point. Think about it. If x is 0, which is how we find a y-intercept, we would get y equals a times b to the 0. And anything to the 0 is 1, right? So this just equals a. Therefore, a is the y-intercept. So whatever number comes first in our exponential general form, that's our y-intercept. B is kind of like the rate of change. And that's more of like a sequence and series term. But if you've learned anything about sequence and series, an exponential function is the exact same as a geometric sequence. When you take one step to the right, you're going to multiply by a constant amount with each step. This is like what we will multiply by. So this first example, you can see 4 times 2 to the x. This means we're going to double. Each time we move one step to the right, we're going to double. Each time we move one step to the left, we're going to cut it in half. We're going to opposite of double. Okay, so let's graph this first one. It has a starting point, a y-intercept of 4. With each step to the right, it doubles. So if I plug in 1, I get 4 times 2 to the 1, which is 8. If I go one more step over to 2, I get to 16. And then my next step would be 32, and that's way off the charts. Moving to the left, I'm going to cut it in half. So if 0 is 4, negative 1 would be 2, negative 2 would be 1, negative 3 would be a half, then a fourth, and then the dots pretty much just sit right above the axis with smaller and smaller fractions each time. Okay, think about why that works. If I have 4 times 2 to the negative third, that's the same as 4 over 2 to the third, which is 4 over 8, or 1/2. Okay, so that's why that goes that way in terms of the negative exponents. All right, so my two important parts to drawing this graph are where does it start and what does it multiply by going to the right and divide by going to the left. And each one of these graphs should have a horizontal asymptote. Okay, if it hasn't been shifted up or down, that horizontal asymptote should be the x-axis. Because think about it, how could an exponential function ever be negative? In this case, y equals 0 for the x-axis. Okay, making your x negative doesn't make the function negative, it makes the function a smaller positive value. So there's a nice standard easy 4 times 2 to the x. This is an example of exponential growth. Exponential decay is just the opposite of that. I'll have some examples, some models of both of these. Exponential growth is what your money does when you put it in the bank, or what populations of countries do and things like that. Exponential decay, you'll learn about in science with half-lives and some radioactive material. If you leave it sitting out, it just decays, it just slowly disappears. This is what we use exponential decay models for. Okay, so 4 is still the starting value. So to graph this thing, I'm still going to start at 4. This time I'm going to multiply by 1/2 with every step to the right. So these are just complete mirror images of each other, my two graphs. And then I'm going to double as I move to the left, 8, 16, and then again I'm off the charts. Horizontal asymptote, still y equals 0. That applies over here too. And that's exponential decay. All right, so no big deal. I double moving right on exponential growth. I've cut it in half, which I'm still multiplying. But when you multiply by a fraction, it might be simpler to think of it as dividing. Either way is fine. So these are nice basic ones. But as we know, it can't stay that easy. We need to twist and turn and shift and shrink and stretch these graphs. And then we can graph any exponential. All right, so let's see how this one has been changed. The transformations or translations that we have done in the past, they are still going to apply. So think about your base function. It looks like 2 to the x was the base function. And then look and see what has happened to it. Okay, I have a stretch times 5. Okay, so original points are going to be 5 times higher than they were before. All right, a 5 times stretch. I have x plus 1. That is a change that has happened to x. So that's a horizontal. This is a horizontal shift. And remember, x things go the opposite. If it's plus 1, then that's left 1. I have a minus 2 on the end, and that's happening to the entire function. Basically, that's happening to y. So that is a vertical shift down 2. All right, so let's see how all those things play out in the graph. Originally, it was 2 to the x. So let me just pick a light color and put 2 to the x in there. 2 to the x starts at 2, or excuse me, it starts at 1. Then it goes to 2, 2 to the first, 2 squared, 2 to the third, 2 to the fourth. And going the other way, it's 1/2, 1/4, and so on. So here's my original lightly. Hopefully you can see that light blue in there. And let's apply these changes. If you ever, just before I start, if you ever get stuck and you're worried if your graph is in the right place, I cannot stress enough. A graph is XY points. Substitute in any X you want and make sure that it works, and your graph will be good. Okay, so if you remember your translations, or transformations to graphs, remember we shift last. So let's kind of take a few of these key points and apply the transformations a point at a time and get an outline for what our new graph will look like. And I'm going to shift last. So let me take our kind of intercept, our starting point, which is at 0, 1. First, I want to stretch it times 5. And 1 times 5 is 5, so that takes me to here. And then I'm going to move it left 2 and down, left 1 and down 2. So here we go. So the original point, my original starting point is there. With these points that are approaching the axis, it's kind of hard to do that times 5, but we can handle it. Let's do the point for that was originally 1/4. So I'll get a new color. This point right here was originally 1/4. So 5 times that is 5/4, which is 1 1/4. So there's that. So that's 5 times taller. That's the stretch times 5. Then left 1 and down 2, left 1, down 1, 2. Here's that one. All right, so that point actually went down, and that has to do with the times 5. A times 5 on 1 is a bigger effect than a times 5 on a 1/4. All right, so there's a new dot. I'll kind of make my new dots big and bold. And then let's do one more, and we should get an idea. One thing we know for sure that's going to happen is the shift that's going to change our asymptote is the down 2. So my x-axis is originally the asymptote. I'm going to go ahead and move that down 2 and get a framework. I haven't twisted this or flipped it, so I'm going to still have the general swooping up motion. I'm just kind of stretching it out taller. Okay, so now I'll do a black dot. Let's take the original dot that was here at 2, 4. All right, height of 4 times 5 gives me a height of 20. So that's a huge increase, and that would take me up to about here, up off the top. And then a left 1 and a down 2 should take me to right there. And one more. Let me do this point 2. Originally, height was 2. Stretch times 5 takes me to 10. Left 1, down 2. So all of those points together will give me my new graph. Approach the asymptote, and not the open circles, but the bold, different colored circles. That's my new graph. So that's how we apply our transformations to this graph. So I could ask you domain and range. The domain on most of these is going to be all real numbers. Because it moves forever to the left and the right. It moves slowly to the right because it's so steep, but it will go, there's no x I can't sub in. The range, however, will be only above the horizontal asymptote. So the horizontal asymptote is y is -2, so I don't reach that, so I just need to be greater than -2. All right, so there's not a whole lot more to ask about it, but this is mostly a review of our translations, applying them to this new type of graph. Okay, so here's what I want you to do. Write this one down, pause your video, and try to graph this, and then when you resume, I'll have the answer for you, and you can compare what you did. Okay, so here we are. Here are the things that happened. Our original graph would have been 1/2 to the x, and I've drawn over here on the right what 1/2 to the x looks like. As far as the transformations go, this is a ×3. A vertical flip, that -3 at the front does both of those things. It stretches it ×3 and it flips it vertically, and then a right 2 and a down 2. So it's kind of tough to take that full line and apply those to it without doing it point by point. So I want you to really think about this a point at a time. The vertical asymptote, by the way, which is not vertical, it's horizontal. Horizontal asymptote is at 2, or -2, because of the down 2. We know that for sure. So let's just go a point at a time, and these are color-coded. The green dot was originally at -2, 4. Okay, now let's apply the translations to that green dot. Its height is 4. A stretch of ×3 gives it a height of 12. A vertical flip gives it a height of -12. So at this point, I'm at -2, -12 from way up top off this graph. Then the right 2, down 2, no big deal. Okay, I couldn't show the being up had a height of 12 because of my axis, but that's how I got from that green dot over here to that green dot over here on my graph. Okay, so the same thing happens. The red dot. The red one has a height of 1. So I'm at 0, 1. ×3, I'm at 0, 3. Vertical flip, I'm at 0, -3, right here. Right 2, down 2. There we go. The original blue dot was at 1, 1/2. ×3, I'm at 1, 3/2, or 1, 1.5. Vertical flip, I'm at 1, -1.5. Right 2, down 2. And there we go. So that's just 3 selected ones, but that's enough. And again, on your final graph, the way I confirmed those was by plugging in the x values. If I substitute in 0 to my equation after it's been transformed, I get -3 times 1/2 to the -2 minus 2. 1/2 to the -2 is 4. Think about that. It flips it over because it's negative. So that's -3 times 4 minus 2, which is -12 minus 2, or -14. Your final graph should never it should sort of never be wrong if you're willing to plug in the x's and c. And you could do that for the same for the other ones. Last thing quickly, can we take a graph and come up with the equation? And for the sake of time, I'm going to pause this one again. Pause with me now, write the equation, and then when you resume, you'll have the answer. All right, this one turned out to be pretty complicated, and I think what's going to make it manageable is if I tell you that that point right there was our original intercept. So the answer is down here at the bottom. Let me talk through how I got all of these translations. Okay, first of all, what I can tell over here by these numbers in green is that my base is 2. If I have, I've put in red dots the points that go through nice integer intersections of our grid lines. If I increase from 3 to 6, then I know that my base is 2. Okay, so that gives me 2 to the x. So 2 to the x goes through 0, 1, and then starts doubling, right? It goes up here like this. If I tell you that that red dot was my old intercept, let's talk about how we got from the original intercept, the old one, to the new one. Okay, so let's work our way backwards. That point, I know it's moved up 1. Okay, so that's because of the asymptote. The new horizontal asymptote is 1, so I know this thing has a +1 on the end. If you know this used to be the intercept, that means it had to be moved up 1 and left 2, which means it was here 1 step ago. All right, it went left 2 because it went from the axis over to -2, and it went up 1 because we know the whole thing is shifted up 1. Okay, so there's how I get the x + 2 and the +1. But in order to get from the old intercept to there with a vertical flip, I had to come from +3. +3 down to here to -3. So all those things put together, I think is enough info. How did I know +2? Because the point went from the axis over to our new dot here in red. How did I get the negative? Well, obviously this thing has been flipped over. How do I get the 3? Well, if the shifts of a 2 left and a 1 up go from this dot to this dot, then it had to start here, and that means it's at -3, which means it had to be flipped from +3. And I know that was a lot, and that's pretty confusing for this last 2 minutes of this video, but that's how we can get to this from the graph, but that's based on knowing that point used to be our intercept. So we'll spend some more time on these in class, but I just wanted to get one quick one in before the end. If it's a little fuzzy still, don't worry, we'll talk more about it. Young out.